Welcome everyone to the second webinar in our series. What I think you'll see here is that we've got a full agenda. My intention here is to continue from where we left off on the first agenda and provide more in-depth information on how and what needs to really be implemented to successfully deploy a session border control in a cloud environment. And again, the reason for that is because we enable real-time communications in the cloud environment. So with that, let me go ahead and jump right into it. First, let me recap from our last webinar, give you guys just a heads up on what we talked about there in case anyone can't remember the key points we had. So the VNF software market is going to be a pretty big market, $15.5 billion by the end of 2021. And 25% of that software markets can be represented by IMS, SBCs, diameter signaling controllers. That's sourced from IHS markets. So it's an important segment. It's an important thing that we believe that our customers want to understand how to get there. The SBC VNF revenue, the revenue associated with session border controllers as a virtual network function, will grow from 40% in this year to 76%. And that's as a percentage of total SBC revenue. So the physical hardware appliance portion is going down and the software only version is going up. Clearly, as I mentioned last time, the market is in movement. People are implementing things already. There's an opportunity here for people on the webinar to take advantage of that industry learning curve and to jumpstart the path to NFV. There's a lot of good learnings that are going on. I'll share some of ours today, and I think that's really a big help to people who are looking to move going forward. We talked about several cloud myths for virtualization, security, performance, load balancing, and reliability. And the point there was we'll be aware of what those cloud myths are and focus really on what's actually a reality. And as we said last time, a cloud native SBC, something that's designed to operate in the cloud, can deliver the success criteria that are needed to enable real-time communications in the cloud. So with that, let's go ahead and jump into today's content. One of the last things I discussed in the prior webinar was that a well-designed cloud-native SBC is built on several important factors. And one of the most important ones is this architectural approach called microservices. So what microservices is, at a simple explanation level, is an application that might have previously been built in a monolithic services architecture where everything is all bundled into one piece of software. Microservices now takes that and breaks it into loosely coupled components. So instead, each of these pieces can then be separate and managed separately, yet they provide together an application. So that's shown on the right-hand side, where a series of functions is broken out, and together they make up whatever application is being used here. With this modularity comes a lot of benefits. The independent scalability of each of the microservices, the ability to replace those components with new software or to just upgrade them independently, and being able to isolate and make changes in terms of technology choices. However, there is a bit of a complication. It's not really important that you can't be overcome, and I'll talk about how we did it. It does add the complexity that now each of these software components are talking to each other. In a monolithic services design, they already were talking to each other just kind of underneath the covers. Now they're talking to each other through APIs, and there's things that have to be handled. So what actually has to happen? Well, as we went through our journey to microservices, we learned a couple really important things, and I want to share those here now. First and foremost was really being able to take a hard look at that underlying architecture and make those decisions on how granular you want to break down your function or your application into microservices. That granularity becomes really important because the priority here is that you have a trade-off between the chattiness of the intercommunications, the intercomponent communications, and the scalability of the solution. And what we found is some technology choices look good on paper, but you really got to do prototyping at scale to really understand how that behavior works. And so when we looked at, and I'll get it more into details on what we did, but when we looked at it, we had a bit of an advantage. We had already architected our physical session border controller into functional components that were already discretely implemented. It's just nobody knew that because it was all under the covers. So for us, it was a really relatively straightforward choice to break things out, but we still had to manage this trade-off between chattiness and scalability. The other thing we learned was about process change. So we found that as we exposed more of these internal functions, our operations teams and ultimately our customers' operations teams became more dependent upon the design team to take care of some system level functions, automated discovery, self-control behavior, things that were going to be important to make that microservices version of, in this case, an SBC, work properly, work without a lot of overhead burden, right? And to give the operations teams the ability to control that behavior rather than expect them to figure out how each of these component pieces were working from the ground up. This is in line with, if you've heard the term DevOps, this is in line with aligning the design and the operations in the software model so that they work better together. So absolutely we believe in that model. So what we did, as I said, was we took our session border controller, broke it out into microservices model, and we really wanted to drive to these three attributes of the value to the customer, right? It's not just what we were able to do, but why is this valuable to ultimately to our customers? So it drives efficiency. As our customers scale services, they only require the resources they actually use. You no longer have to buy resources and have them sit around and not be utilized. Future-proof. I mean, people like to say that, and it is a bit of a term that catches a lot of ground, if you will. But for us, it really means we're being able to replace the individual microservices with technology choices without disrupting the entire service. And I'll show you an example of that later on in this webinar. And finally, agility. For our customers to now be able to react quicker to in-service demand and changes for service functional requirements. So we've looked at these things and we've said, how can we make a better product that operates more efficiently and effectively in the cloud and solves problems that our customers might face down the road? This is what it looks like from a session border controller. So as I said, we kind of had an advantage here. We already had signaling, media handling, and transcoding operating somewhat independently under the covers. Now they are truly independent operations with communications between those three domains. And we can now orchestrate and instantiate individual VNFs or virtual network functions for signaling, for media, and for transcoding. They don't have to follow the scalability of you turn up one, you have to turn up one more of each of the others. It also means, as I said, you have independent technology choices, and overall you have independent scalability because these functions do not scale linearly with each other. And so we took advantage of this architecture to be able to drive this forward and benefit our customers. So I want to slightly change topics now and talk about the ETSI framework. So ETSI was the European Telecommunications Standard Institute, and they've developed a framework for network function virtualization. Complicated picture shown here on the right. I am not going to try and go through it in detail. I do want to make that clear. But I will break it down and show you how things work. So at the top layer, you have an orchestration layer, which is responsible for the onboarding and the lifecycle management of network services. And overall, managing overall virtual network function, the packages. This is at a higher abstract layer than the individual VNFs themselves, in which case we're showing the EMS function and element management function that participates in managing those VNFs, and the VNF manager itself that communicates upstream with the orchestrator, communicates horizontally, if you will, with the element management functions, and communicates down into the virtualized infrastructure management. The VNFs themselves are the specific network functions that run on one or more virtual machines on top of what's below it, which is the NFV infrastructure. As you'll see, and I'll go through this, you'll see this is where we've talked a lot about this SBC and the different VNFs, so that's kind of where we'll focus a lot of this conversation. And then finally, you have the virtualization layer, the virtual infrastructure manager on the right, and managing those actual virtual computing, storage, and network resources that still run on some physical devices, commercial platforms, commercial storage, and commercial hardware. So let me, from there, jump into where we are, right? So we have a VNF manager and an EMS, and we have a session border controller that we'll talk about here today as a virtual network function. But that's actually only part of an overall portfolio. We have several other VNFs currently deployed in this model, and we will be adding more as we go. I think what's important is that even though these are the piece parts we play in, the actual orchestrator at the top right, the virtual infrastructure manager on the bottom right, and the NFV infrastructure, the components on the bottom, actually really are made up of multiple vendors. And it's truly an NFV ecosystem where we need to be working with other vendors and other suppliers to test and verify our solutions. So when our customers come and are looking for products, and we have an answer as to how this would work. It's been tested. We know who we've done this with. We know who we can tell you and point to working examples of how this operates. Just one last point, because I will come back to this subject. I mentioned it in the first webinar as well. The de facto choice for telecom applications is OpenStack, which is a free open source software platform for controlling these pools of compute, storage, and networking resources. And you'll hear, if you look and see who provides these OpenStack distributions, it's not the actual OpenStack community itself. That is a very robust community of developers and people, including us and many other vendors, providing inputs, but it's actually commercial distributions from companies like Red Hat, Canonical, and Wind River, etc., who actually will take the open source releases and turn them into commercial distributions, providing packaging, testing, and support for these open source products. So the reason I listed those three is because those are all three that we've currently worked with in the past. So we've got microservices as an important component of why NFV works. We've got an infrastructure or a framework, this ETSI framework that it fits within. But ultimately, you actually have to do the hard work and develop stuff. And one of the things that we looked at as we went through this process was, you know, there's areas that things aren't quite the same between the web applications and telco cloud or real-time communication applications. So let's talk a bit about that. And then what are those attributes that we had to look at and say, how can we innovate? How can we make things better? How can we actually make it so these things operate really well and make it beneficial ultimately to our customers? So that's what I'm going to cover here in the next section. So as I said, there are commercial distributions of virtualized software, and I mentioned OpenStack being what's predominantly being used today by the telecom industry. The web cloud domain, the applications that run in the web, and the attributes of those web applications are not the same as real-time communications running in a telecommunications environment. And I've listed a series of attributes here, but I'll just run through a couple of them. One of them is stateless versus stateful. Much of the data traffic, you don't care about the state of the data traffic, you care about the packets arriving. In real-time communications, you care about the state of the session, right? TCP and UDP. So TCP guarantees the recipient will receive the packets in the order they were sent. UDP does not have error checking and no guarantees of packet delivery. Ideally, that's actually good for real-time communications because without this extra overhead of overchecking, the transmissions of packets is quicker, which is good for delay-sensitive and latency-sensitive applications like real-time communications. So again, but it makes a difference on how you handle the packets when you're doing real-time communications. One of the other ones to talk about here is TLS versus IPsec. So TLS is suitable for web applications and e-commerce, but does not support UDP. So TLS as a security solution is not used, but things like IPsec are. And again, if you look at the rest of these, I mean, you run really into this queued versus instantaneous attributes. right? Data services, many packets can be queued up. It doesn't affect the quality of that service. It doesn't really ring true in a real-time communication service. You really need instantaneous communication. So as I'll go through and talk about some of these innovations, these are innovations that were driven by these characteristics and by operational characteristics for our customers. So with that, let's go ahead and move on. So runtime ready. I mentioned this in the initial webinar as well. Runtime ready is clearly a place that drives value, huge value in our opinion, ultimately to our customers. So runtime ready means that when a virtual network function is instantiated, it's ready to accept traffic and perform its function without needing additional manual configuration. It means the ability to have auto registration, auto configuration. It means that the configuration that has to be turned up for that virtual network function is available. Without it, you will not achieve the responsiveness that you're looking for service velocity, and you certainly won't achieve operational efficiencies if you have to do things like manual configuration. So how does this actually work? So at the orchestration level and at the VNFM, the VNF manager level, there's an on-demand request for the instantiation of a VNF. At that point, that virtual network function needs to auto-register. It needs to grab and be told what its licensing is. It needs to be told what its configuration is. When that's done, it's now, quote, step 4 here, runtime ready. And then finally, that information has to get back up to the VNF manager so it can do things like update the DNS directories. This process happens in just a few minutes. So literally a session border controller, a virtual network function that is instantiated to provide a session border control function and network can now be turned up in a matter of minutes. Flexible load balancing. As I mentioned, again, web apps versus real-time communications. DNS, which is the dominant load balancing mechanism in the web app world, isn't really going to necessarily be the best solution in the real-time communications world, partly because it's not stateful aware. So load balancing in this cloud architecture is the process of distributing the workloads across multiple instances and being able to handle variances in traffic so that you optimize things like server capacity rather than overbuilding capacity. It increases solution resiliency, right? Because now if I have a server that's overloaded or I have a server that may potentially fail, I can rebalance traffic and not lose any traffic. It enables me to actually, load balancing is to failover, or I'll get to that in a bit more detail, but load balancing allows me to manage failovers gracefully. So overall, load balancing is kind of really an important thing. Well, again, if DNS isn't really the right solution, and for that matter, we also looked at SIP front-end load balancing, what did we really want to do? So let me show you why DNS didn't really work, and I'm going to move on to the next slide, and I'll show you what we did to figure this out. So imagine a SBC in your network on the left. A peer network SBC wants to send traffic to you. It does a DNS lookup, and it gets back a DNS response, and it says, oh, send your next SIP invite over to this SBC, which is now actually a virtual network function in a cluster of VNFs. The problem is that traffic probably shouldn't have gone to that one because that's the next SBC available in lookup table, but it's busy. And the invite probably should have been sent to a different VNF, but DNS didn't know that because it's not stateful aware. In fact, that invite probably should have gone to this other virtual network function instantiation. So how do we make that happen? How do we provide a next level of innovation to make this happen and still interwork with traditional DNS? And that's what we did here. Now, if you look at the same picture, the picture looks the same, except inside that SBC VNF cluster, we've expanded it. We now have stateful knowledge of sessions being exchanged in this resilient, lightweight method between the individual VNFs so that there's an intelligence here of which VNF should be getting the next piece of traffic to balance the load optimally across all of these VNF instances. So if I can put it in slightly different terms, now all of these instances are coordinated so they act like a large adaptable application, so traffic gets redirected to underutilized instances within this cluster. And yet from the external side, it still looks the way it should look so things work properly. So what does that look like? Well, we start here, the same 3 steps. I get a SIP invite that comes over. What instead happens though, instead of taking that traffic where it's overloaded, I now will do a SIP redirect. And I will actually tell it, no, send your traffic over to this virtual instance. This can solve multiple problems, and I'll talk a bit about it when I get to reliability, but the fact is this is how a second layer or second level of load balancing and load balancing information can be managed to optimize how traffic is being handled in a cloud environment. Okay, this is not something that everybody does, and we feel really that it's critical that this happens to, as I said earlier, to optimize the efficiency of a network and the application of using virtual network resources. So with that, let me jump on. I've mentioned it a couple times over to redundancy and reliability. So one of the other things that we looked at was high availability for media VNFs. And what we have as a solution, you can see here there are 5 instances of this SBC that are really a media SBC, and it's in an N-to-1, or in this case a 4-to-1 redundancy model for service availability. So what's missing here is these are just the virtual instances. There's no information, there's no control system. Okay, that's the key that makes all this work. So the idea, and again, it's already the same as what I showed earlier for runtime ready. You have a configurator, you have licensing, you have a VNF manager. All of those things need to have knowledge, especially the VNF manager needs the knowledge to define the redundancy groups for instantiation, for healing, and for fault management. It has to have stable knowledge of the sessions for each of the SBC VNFs. And so when one of these VNF instances might fail, right, it has to know how the traffic gets automated and picked up, right? This all should be synced up so that each of the instances knows how to pick up traffic when one of the instances fails. And I said earlier that web apps don't necessarily equal real-time communications. Typical web apps use a solution called floating IP address, which basically says if I'm sending traffic to this IP address and it's not available, send it to its associated or the next IP address in the table, if you will. The problem with that is it's not rapid enough. It doesn't meet the latency requirements for real-time communications. So instead, we went and used a new solution that was defined, again, by the OpenStack community called allowed address pair, where traffic is actually sent to one of these instances, and if the instance doesn't respond, traffic is sent to its mate or this allowed address pair, or in this case, it's sent off to multiple of these address pairs in this N-to-1 redundancy, but only one of them picks up the traffic, and that again is managed by the knowledge of what's going on and which is the right instance to be picking up traffic. So again, some significant innovation to make this work and to absolutely be sure that we can provide high availability and reliable solutions that our customers need to deploy in the cloud. So we've talked about runtime ready, we've talked about load balancing, we've talked about redundancy and high availability. The other one I want to talk about is performance. So there's 2 performance characteristics I want to talk about. One is shown here on this slide, which is a couple examples of how to tune OpenStack to optimize how packets are handled. And the second one on the next slide, I'll talk about the introduction of using graphical processing units, or GPUs, for transcoding. So let me go back and touch on OpenStack. Open source community software taken by, again, these commercial distribution houses and made available to people like us to use. And yet, OpenStack by itself has a series of proposed configurations, and people have to set that up to optimize for their specific application. And when we looked at the issues, if you will, or the ways to optimize real-time communications, we ran into what's shown in this chart here. We needed deterministic behavior for packet handling because that lowers packet processing latency, which increases system performance and capacity. And we were driven, and I'll be forthright in saying this, we were driven by customer requirements that said you need to hit performance levels in the cloud that are equal to or better than performance levels we could get when we were previously buying hardware. And so we looked at how we were going to accomplish this. And there are a number of ways we looked at and have now optimized OpenStack configurations. But I just want to focus on two of them here. Because we looked at these and we said by ensuring this deterministic packet behavior, we can actually increase or decrease the packet processing latency by up to 50%, which will increase performance and capacity. And yes, these do come at a bit of a cost, if you will, a virtual resource cost. So I'll talk a bit about that. So NUMA awareness. Basically, again, to boil this down into simple English, this is the best way I can understand it, is it means allocating memory per virtual machine rather than using a pooled memory so that you avoid unintended memory access issues. While this does cost a bit more in terms of the virtual resource, the memory virtual resource, it's more than offset by the efficiency gains in processing because I don't have memory access problems. I'm not waiting to get access to a piece of memory to do something. CPU pinning, something similar. And here we're allocating or pinning, that's where the term comes from, virtual compute resources to a specific host CPU or a virtual machine. So again, this adds some cost in terms of the virtual compute resources being allocated, but it's more than offset by the gains from not having processing bottlenecks in having available compute resources when you need them. We did a bunch of measurements. We looked at this. We looked at how to hit the performance levels we were being asked to hit. And these were the two largest drivers. As I said, there's 3 or 4 others that also contribute. The other thing we looked at from performance, and now I want to go back and touch on microservices, right? You can see how all of these things fit together, was that we looked at transcoding. And we looked at, is there a better technology choice for transcoding rather than using CPUs or normal compute processing that people expect to see in servers. And when we looked at GPUs, we realized pretty early on that there was a huge opportunity here using GPUs because they're built to handle high volume, complex parallel processing. And media processing is one of the most complex processing items to do in a session border controller. So we were looking at ways to achieve performance that was as good as digital signaling processors that are typically found in hardware appliances and would be far better than CPUs to be able to hit, again, the types of performance and scale that we were being asked to provide. So this chart on the left, the purple is CPUs and the blue is a GPU from a company called NVIDIA. And what you can see there is a significant increase in the number of sessions that can be handled by GPUs. On the right, though, again, purple is still the CPUs and blue is the GPUs, but this is now comparing the cost per session. So while a GPU costs more than a CPU, the amount of processing it can handle is substantially greater, meaning that the cost per session is substantially less. So the line on the right-hand side is showing the savings. So you get significant savings. Now, it's not, across all different codec types. And that's some of the innovation and optimization that has to be done as to how each codec type gets handled. But we looked at this and we said, this is an important factor. It may or may not be an important factor to every customer, but it was important for us to be able to understand how to apply technology choices and be able to show that microservices enables these and provides more benefit to our customers. So with that, I'm going to stop. I'm going to turn it back over to Lance. And Lance, if we can run the poll question.
Sure, Dan. I'm launching that poll right now, so you should see that pop onto your screen. Which characteristics of innovation, or which characteristic of innovation is most important to your decisions for NFV deployment? You see you've got 5 choices right there: runtime ready, flexible load balancing, high availability, performance enhancements, or of course none of those. So we'll take a couple minutes to kind of sit here and let some folks vote there. While we're waiting on that, I do want to remind everybody about the download that's on the right side of your interface. Little document icon is our microservices white paper, so check that out if you haven't yet. In addition, I want to just remind everyone to ask your questions. We have Elizabeth Page, Director of IOC Sales, on with us. Of course, Dan is on, and they're standing by to see these questions that you have, and they can help you out with any questions you might have. So, Dan, I'm sure you're taking a look at some of those results coming in. We've had about a quarter of the audience vote so far. Anything you want to reflect on as those come in?
I'm pretty shocked that everything's important. That's actually a good thing. And that nobody voted for none of these. So let me just let this run. So we're looking at runtime ready and high availability at 30% right now, and flexible load balancing and performance at 20%. So, I mean, I think I want to say, you know, we were smart. We focused on problems that we thought were important to our customers, and those are the ones we've been addressing. And it seems like people are saying that all of these things are important, or at least relatively speaking, they're all important. So with that, let me go ahead and jump forward here to here. So, you know, I think, and I used this to conclude the first webinar. I'll use it again here. I think what's important is not the technology necessarily, although it probably is nice to understand that we've taken the challenge and solved the hard problems, but that you align real-time communications business goals with cloud network priorities, with implementing network function virtualization, right? Understand the realities of deploying a virtual SBC. You know, avoid those myths, right? Determine where there's the best solutions possible to do this, and then go ahead and do it, right? Enable real-time communications in the clouds. Make sure that it's secure, and make sure that it interworks with everything else by having SBCs that have been designed to fit there. I mean, ultimately, as far as I'm concerned, you know, and I said this last time, right? There's a learning curve, and people have to go through it. We've been through it. We can help you jump over some of the steps, but people are going to move at whatever is their own pace, and that's fine. But it's getting on that path and moving forward, and being confident that this is all happening. It's happening out there in the network, and I think for the people in the audience, you know, it's available when you guys are ready to move. So with that, I'm going to put this up and just point out that we do have a webinar replay from the first webinar. We do have some links on our website to learn more about virtual network functions and about our cloud native SBC. And as Lance had said at the beginning, there is a white paper if you want to download it on microservices. With that, actually, Lance, let me push it back to you and say, do we have any questions we want to take a look at?
Yeah, Dan, we sure do. There's a couple that came in, so I'll just go from top to bottom. The first one, with microservices, how granular should you get to break down application functions? So I guess how granular can you or should you be able to break down the app functions?
Good question. So, and there is no easy answer. As I said, in our journey, we did a lot of design work, we did a lot of prototyping, and we did have a bit of an advantage that we had already an architecture that lent itself to the 3 ways we broke it out. But ultimately, I want to go back and touch on that point I made earlier. It's a trade-off between scalability and chattiness or the inter-component communications. So it may be that a component that receives information and executes independently, like, for example, if you had a application where you had a billing component of it, you might be able to break that out and make that separate very easily. If you had a application that had some operations functions in it, you clearly want to break that out. You don't want every other VNF function doing the operations that can be combined. So again, it's breaking out the things that make sense and then ensuring that that product can scale appropriately. So I wish I had a simple answer, but it really does come down to architecture and design work.
Okay, very good. Next question was about the ETSI model. Is the ETSI model for NFV the only one, or are there other frameworks for how the NFV work?
The ETSI model is not the only model. There's some good news though. So one of the other models for NFV and for the whole infrastructure and a lot of the focus on the management and operations side, the MANO side, is being driven by an industry group called ONAP. The good news there is ONAP and ETSI have begun to work together and now actually have integrated their models so that people who have a focus in one area or the other can now more seamlessly interoperate with people who might have started at a different point. We started at the ETSI model. That's where our customers asked us to be. We are actually part of the industry organizations that's driving ONAP, and we are doing incremental development to fit into both of those models. I should mention also there's things like Amazon. AWS, or Amazon Web Services, doesn't use either of these models. They actually built everything themselves. So if you're looking to deploy a session border controller in the Amazon cloud, which is doable, it's something we support, it's something other people support, it has to operate under Amazon's rules. So again, having a framework of how things are built and how things work and how they interoperate with things around them is the key to making deployment success.
Okay, thanks for that, Dan. Here's another one about the runtime readiness, which was, one of the characteristics that the audience said was most important to them about NFV. So the question is, when an SBC VNF is instantiated, how quickly is it actually runtime ready?
So I mentioned earlier, this can be done in minutes. It might sound like a dream, but it is true. We actually have the proof points for that. As long as you're instantiating an SBC that has an available configuration, as long as there's available licensing, the auto registration, auto config process, and the actual, I will say the implementation time, that is on the compute module, downloading the information you need, having it available in memory, implementing it, and then, quote, coming up or being available and being recognized, for the example in the load balancing example, being recognized by the other components in a cluster or the VNFs in a cluster, the VNF manager, knowing that it's now available. All of that can take place in a matter of minutes. It's under 5 minutes.
Okay. Pretty quick. All right. Last question we have for today. If I have only a small percentage of traffic that is transcoded, does it still use GPUs?
It doesn't have to. Again, using CPUs for transcoding has been the default model until recently, until we've actually introduced support for GPUs. They work. They just don't scale very well. You need a lot more compute resources to scale transcoding. So if you have a small amount, if you have a location that doesn't need much, or an application where it doesn't really require transcoding, then no, you probably can run that on CPUs. You'd still be running it in this virtual network function world. You still could break out the VNF for transcoding different than the VNF for signaling and the VNF for media, because they don't have to scale at the same point. Matter of fact, if you needed no instantiation of a transcoding VNF, you just wouldn't do that. If everything was passed through media and there was no transcoding, or everything that the traffic that was handled was of the same codec type, then you just have signaling media VNFs and no transcoding VNFs at all. So no, you don't have to use GPUs.
Plenty of ways to find out more about all this. Make sure you download that piece of collateral there, that white paper. If you have questions that come up later after the webinar, you can always contact us online. There's contact forms all over the place on our website. As always, you can reach out to us personally as well when you get one of our emails with the replay. So that'll be coming out this afternoon. And again, we thank you for your time, and we look forward to speaking with you in here in the near future. Take care and have a great day.